you should talk about atmospheric compensation, because what we want to do is a physical analysis of our signal instead of just correcting something which is wrong. So that's why I rather like the term compensation in what's done using MOTRAN for atmospheric correction. And why do we do that? So we want to have ground information, and there is a lot of influence of the atmosphere. That's what I outlined yesterday. And we should have some spectral albedo of the ground, or some singular spectra of our material to identify it against any reference from laboratory. So this is the one part of atmospheric correction. And of course, if you want to do vicarious calibration and validation, you want to being able to compare to a reference on the ground and to see if everything performs as expected. So that's the goal. And now, just to distinguish between MOTRAN and atmospheric compensation. So MOTRAN is forward simulation. This means you have this number of inputs I showed yesterday, and what you get is at sensor signal. So it's kind of a straightforward simulation. And so from the, in fact, from the reflectance data, you get to the at sensor radiance. This is how it may look in a spectral range. And for the inversion, so if you do atmospheric compensation, you start with the signal at the sensor, which should be calibrated. And from this signal, you want to invert for a variety of inputs. So you, in fact, you have an underdefined system. So you have to, just one signal, and you have a very broad variety of inputs. And you have to think about which inputs are relevant and which ones can be kept stable, and which are known from other sources than from the image data themselves. So the inversion process from signal to reflectance is kind of more complicated than the forward simulation, because you don't know, in fact, it's really underdefined. So you have too many unknowns. And that's why MOTRAN itself cannot do the inversion. That's one thing which is always sometimes not understood well. So MOTRAN does a forward, but it doesn't do the search for the correct input parameters. So you have to deal with lookup tables and whatever to solve that. So that's the backward. So for atmospheric compensation, what you have is, well, from our side, we do it with ATCOR of our satellites. I guess you know this package. And in ENVI, you may have flash. I don't know if you have the flash in ENVI. Do you have it?
Yes, we do.
Do you have any other atmospheric correction package, like in ERDAS or in?
I'm not sure for ERDAS, but ENVI, yes, we do have the flash. Okay,
but I think you don't have the ATCOR. But yeah, anyhow, and in ERDAS, the ones from our side are the ATCOR modules, the one directly from us, or if you get it from ERDAS, it's the same as, so it's also developed from our side. And in Geomatica, they also have an ATCOR module, which is developed by them using the same physics behind. So that's just to give you an overview of these packages. There are not many other available codes for atmospheric compensation, so it's kind of limited what you can get. Some people are writing their own, and there is a way to invert it. That's something I show you later, using the MOTRAN outputs directly. So that's something which is included in the Modo as well. There is a lot of features. I don't go through this list of features. Major difference maybe to flash in ATCOR is the consideration of the terrain. So ATCOR does the terrain correction and flash does not. And the second maybe difference is that ATCOR has the full batch, but in the meantime, I think flash can also do full batch processing for satellites. but that's these are maybe the most important differences. Maybe some BRDF correction, which is in ATCOR, is of interest, and so on. Then for the reflectance retrieval, we call this compensation in flash or in ATCOR is a physical inversion. So we want to define or find the physics behind our signal. And whereas you can go the easier way, what we call empirical corrections, where you just get, so maybe you know the empirical line method, where you try to relate the reflectance directly to your signal without caring about what's happening in between. So this just assuming a linear relation. I have in the presentation there are now a few slides about empirical retrieval, but I think that's not of relevance for what we do today, so I'll skip those. That's just empirical line correction. Maybe just the summary may be of interest. Why could you do empirical corrections? They're quite easy, so empirical line can be done in a moment, but you don't have the dependencies on the terrain and everything, so you lose accuracy, and you don't estimate the parameters from the image, so you assume everything being constant in the whole image. So that's why physical approaches have some advantages, specifically for satellite imagery. So that's for the empirical. But or is there a comment, or you would want to go more into empirical correction as well? Otherwise, we go into the atmospheric compensation problem. You remember this graph from Motran, and what we want to get is in fact, the yellow curve from everything else. And the correction equation seems to be quite simple. So it's well defined. It's maybe not simple, but we have what we have in the equation is the distance Earth-Sun. We have the adjacency effect, which has to be subtracted, and we have the path scatter radiance, and we have the measured at sensor radiance. So this is the calibrated at sensor radiance, and you subtract these additive terms. This has to be divided by the upward transmittance to get to the ground. And on the ground, you have the ground irradiance term, so the incidence flux, which is defined by the terrain, the diffuse, and the direct irradiance parts. So this is so if you want to do a correction, you have to calculate the irradiance first, and then you have to get the transmittances downward and upwards from Motran, and you got to subtract the atmospheric radiances, path scatter radiances. Where to get the parameters? For Motran, you get the atmospheric correction, atmospheric path radiance, the diffuse irradiance standard, so for hemisphere, and the two transmittances. Then from the geometry down here, you can get the incidence angle, sky view factor, and terrain view. So how much of the terrain and the sky you see, that's a geometric question. And Earth-Sun distance is also a geometric part. Then we know about extraterrestrial irradiance. This can be found from the solar spectrum and the distance. And now there are two terms which are not easily found. That's the adjacency and the terrain irradiance on a pixel. So those need an iteration in the atmospheric correction. So this is the principle how to solve the equation I've shown before, where to get all these parameters from. And as an output of this correction, you get kind of a HDRF, so hemispherical directional reflectance. So you get, I always claim you get what you'd measure if you were on the ground and take the same measurement with the same system. So it's a correction from the sensor to the ground as a reflectance. And how you can do the atmospheric correction, ModeTrend does the forward simulation. So it's coming from reflectance, does a radiative transfer calculation and calculates the radiance. And the atmospheric correction does the inverse from radiance to reflectance. And to do this correction, you need to pre-calculate the expected situations. So you feed in the expected parameter range, for instance, all flight altitude, all ground altitudes, all amounts of aerosol, all amounts of water vapor, and you create a big lookup table which has pre-calculated parameters for atmospheric correction later. So that's what ModeTrend does. So it's really calculation of the lookup tables. That's also done in Flash. They also create a lookup table, and this one is used for the correction afterwards. Even in ModeTrend itself, you can create a really small lookup table, the atmospheric correction parameters, and this will be valid for just one situation and not for all possible situations. And then you can solve from the radiance to the reflectance by accessing the lookup table and under use of the geometric information. So you know for each pixel where it is, what altitude it has, how the slope was, how the terrain was, what sensor you have, and so on. And then you can go for the reflectance retrieval. So this is just the principle of the atmospheric correction. Any question about that? So what's in the lookup table? Yep.
Just a bit. ATCOR is a different module from the one we purchased, right? We only purchased the model version. Is it still accessible from our license? I'm sorry, I'm a bit confusing about ATCOR.
No, I think you only have the model license. So you have the ModeTrend for forward simulation and validation, but ATCOR is a different package. So
okay, yeah.
So this, if you
just to confirm, yeah.
So if you want to process imagery later, it could be done with ATCOR, but you could use Flash, but without terrain correction for that. And yeah.
Okay. Right.
What's in the lookup table? What do we store there? It's the transmittances, the irradiance terms, diffuse and direct or solar flux terms, in fact, should be solar flux here, and the path scattered radiance and the aerosol scattering or spherical albedo. So these are the parameters. It's in fact 7 parameters stored for each situation in 7 dimensions. So in the dimensions are the water vapor amount, aerosols, heights, wavelength, reflectance, and the solar angles. So it makes 6 to 7 or 8 dimensions which have to be stored. And from that you can invert. That's the tricky part of the atmospheric correction, is setting up a lookup table correctly. And in ATCOR, well, you have to reduce, it's quite a process to create it. So you get about 9 GB of data for all situations at high resolution. For the atmospheric correction, what is done inside, and this also applies to Flash, is usually you have to do a classification first. Then you have to retrieve parameters like water vapor and aerosols from the imagery, so you have to know them somewhere from. And then you can remove on the raw data already some haze. So haze and cirrus removal is done by statistics, because this is the white appearance in imagery. And under use of water vapor and aerosols and terrain information, you can get a first order atmospheric compensation. And as I said, you need one iteration on that. So you do it once more with improved adjacency information, so with the reflectance of the surroundings. And then you get a second order atmospheric compensation. And so you get to what we call the bottom of atmosphere directional reflectance, so the HDRF-like product, so hemispherical directional reflectance. I rather like the term bottom of atmosphere reflectance for this output. So this wouldn't be finished yet because this is still directional. So if you want to compare to other measurements, one may have to do the BRDF correction as well. So there is a module which is also part of ATCOR, which does BRDF correction based on the observation angles. I don't go in detail into that one, but it's just to there is a method which uses an external BRDF model, physical BRDF model for correction, and so such that you can get closer to what we call the spectral albedo or the hemispherical reflectance. That's the process. Side outputs may be irradiance maps, classifications, quantifications of water vapor and aerosols, and so on. For ATCOR, it's just we have the spaceborne and airborne version, but I think I don't go into that because for you it's not of relevance yet. Maybe some words about spatial effects. So usually if you look at atmospheric corrected data, you don't see much of an effect in the image. You see a lot of effect in the spectra, in the values you get as an output. But sometimes you have spatial inhomogeneities like the view angle dependencies, cirrus, cloud shadows, terrain, and possibly cast shadows. So if you want to correct those, like the cirrus, if you got the cirrus band, that can be easily removed in the meantime, or you have some haze in the imagery. This is also done by statistical removal. Here is a combination of both haze and cirrus, so this can be calculated from the image as long as you got the cirrus bands available in your imagery. So the 1.37 micron band. Then cloud shadow removal is something we are working on. It works mostly, but it's a critical thing because it's not always working fully automatically. So we have some methods available, and some still have to be improved. But that's for the topographic correction. What we have to consider is really the irradiance from the surroundings, like this. And for each pixel, how much of the sky and of the terrain you see. So these are the two important parts to get the topographic correction done. There's a lot of literature about topographic correction. It's well, of course, it's only critical in terrain. So if you're working in mountain areas, what's also to be mentioned is that topographic correction should consider the BRDF of the topography. So topographic correction cannot be done simply by a cosine correction. So that's why Minayat and all these SCSC and whatever method has been developed, empirical methods which take the terrain into account. And in fact, one would also need a BRDF of the terrain to correct this correctly. Because it's the incidence path is also affected by directional effects. So if you it depends from which angle you illuminate the landscape, and you get a different BRDF effect there as well. So just some outputs of topographic correction. So you should get rid of the terrain somehow, and that's how it looks like in the end. For DM, yeah, that's a radiometric problem. If you have very high resolution instruments like 1 meter, you cannot do easy DM-based corrections. Digital elevation models, you may get artifacts like this one. So in a forest, if you work with surface models, it won't work anymore at high resolution. That's just a side remark. So much about principal spatial effects. Then I got in this presentation I got two sections about water vapor and aerosol retrieval. The question is this of interest for you or not? Otherwise, we can skip that.
I think we should discuss the water vapor and also the aerosol.
Aerosol retrieval. So you would be interested to. Yeah.
Yeah.
Okay. So then I'll go through that one. For the water vapor retrieval, well, of course, one needs water vapor bands. So usually one uses what we call a differential absorption method. So we try to find the transmittance of water vapor from some speckle bands and try to apply this to the whole imagery. And so usually the 940 bands is used with satellites, which has a strong absorption, and you have to compare it to a reference area. So in Sentinel, they have just 2 bands there to get the water vapor right. Of course, with spectrometry, you get a better view of the water vapor, but it works with Sentinel as well. And you do a correction of that by extrapolating from one band or interpolating between 2 bands to the center of the water vapor absorption. And then that's how you get the apparent transmittance of the water vapor. What we also do, we correct for the aerosol influence, because aerosols are scattering here and they add a certain amount of signal, and this needs to be corrected. That's what we call the APTA method. That's what we use in ATCOR, and I think it's also used in Flash. So finally, you get some water vapor amount by relating this absorption to simulations done with Modtran. So with Modtran, you simulate various water vapor amounts, and you get the depth of the absorption from Modtran, and this can be related to the amount of water vapor in kilograms per square meter. Here, in a terrain, it works on open landscapes. It doesn't work over water, because the 940, you don't have signal from the water at 940 nanometers. One could try to get it from the scattered radiance, but that's not accurate enough. Is another output, as you see again, the water, the river cannot be correct. You don't find reasonable water vapor amounts. Also, even in the city, you have a certain influence of these dark objects here. So it's not ideally made, but it's still better to do it that way than doing nothing. There are other methods around, but they only apply to spectroscopy. So like curve fitting techniques, where you try to fit water and leave water and everything else to your signal. I don't go into that one, but in theory it's better. In practice it's slower. That's the problem. Here's one for what they do in NASA JPL in the ATRAM package. ATRAM is also an atmospheric correction software, which is available freely, but it's optimized for spectroscopy systems. I think there are no interfaces to satellite imagery, so you'd have to write it yourselves, but you can get the code from them. But it's open source, and you have to dig in yourselves to get it run. So I think University of Zurich tried to run it, and they didn't succeed yet. So that's for curve fitting and water vapor retrieval. So the principles how we do this. So we get a water vapor map, and this can be used now afterwards for the correction. In multispectral, it will have some influence in the blue because of the Rayleigh scattering, and so it has a certain influence, but not a big one. It has an influence on bands which have water vapor absorptions. So like in the red, it could have an influence, but not much for multispectral. There is one word about what atmospheric correction does in hyperspectral. Well, it's removing the water vapor bands. You see them again. And something which also applies to the multispectral case is the effect in the blue part of the spectrum. So if you have a dark object, like the vegetation here, which is dark in the blue, you get a reduction of the signal because you remove the aerosol scattering. So it's getting lower with atmospheric correction. But if it's a bright object like this red line, atmospheric correction doesn't change the signal. I explained this yesterday. This is this cancelling effect. So you, on one hand, you remove the path scatter radiance, but then you divide by the transmittance of the aerosols. So you also remove the attenuation of the aerosols. So you, on one hand, you decrease the signal, and on the other hand, you increase it again, and then you get apparently the same signal in the blue as before atmospheric correction. So that's nicely visible in this graph. That's just what's done on your data. And of course, if you have bands in the near infrared which are inside this water vapor or are affected by oxygen or water vapor, then you will have a correction of the water vapor on these bands as well. The second thing is I have shown this image first. These are two, well, it's airborne, but the same would apply to satellites. Say the same area detected from two sides. So this sensor has a plus minus 17 degrees, I think, field of view. So it's looking 17 degrees to the sides. That's an angle you easily get with satellites as well in some cases. Or it may be that you tilt your satellite looking to the sides, and so one pixel is viewed with an angular difference of about 10 to 15 degrees. So, and if I'm comparing the signature at this angle, you see the differences here between the two observation angles. And the differences are in a range of 10 to 20% of reflectance. So that's what I explained yesterday, that BRDF can have 10 to 15%. Roughly, you can say it's about the amount of angle of difference. So if you have an angular difference of about 10 degrees, you also get 10% difference, more or less, in average. So that's a rule of thumb, I would say. And so if you have 20 degrees difference, you can get 20% off. At small angles, it's more or less fitting. At larger angles, it will be a little less than the percentage. So BRDF effects are strong. That's something for hyperspeckle. I think I'll skip that one. So what to look at, what to check. Well, maybe the last thing is if you check out the near infrared brightness. So we check out the blue brightness and the near infrared. Your spectra should, or your signature in the near infrared shouldn't exceed 50% if you have vegetation. So that's also a good quality check to see if the spectra are reasonable or if your calibration was good enough. On the other hand, in the blue, it shouldn't go below 0, of course. So, and it shouldn't be really bright. It should be below 10% for normal targets. So that's another check you can do on the data. Now, this is something about spectroscopy. There is a certain air pressure dependency, but only for high resolution spectroscopy. That's also something which can be skipped. But so it's shifting the spectrum. But now to finish up that part, some words about validation and calibration. That's maybe more of your interest. Yeah, let's go into that one. So you said you wanted to do in-flight validation calibration, some terms definition. So what's often done with satellite systems is so-called validation. So they measure in field and they just compare their outputs of their data to get a quality control. but they don't change the calibration constants normally. So it's just to see if something happened to your sensor, to make a periodical check based on ground reference data. It's in-flight validation. If once in a while you see that your calibration is really off from what you expected, then you have to do an in-flight calibration. And the in-flight calibration can be done, well, you want to have new calibration coefficients, so relating the radiance to the reflectance, the digital numbers to the radiance. This is the calibration coefficients. And so the in-flight calibration can be done in two ways. So one is the so-called vicarious calibration. So this means you take laboratory measurement of ground reference targets, or also in-field, could also be in-field measurements. So either you use natural targets, so you go out to the field and take a lot of measurements with a spectrometer and store this and compare to your data. You also can use library spectra of known targets, which is seldomly very well fitting. You could use well-defined reference panels. If you have a high-resolution instrument, you can put up a few meters of a tarp or whatever you have as a reference. Then you can this should have a stable reflectance. So this is just the problem if you have a coarse resolution instrument. It's very hard to find a well-defined reference target in the image. And if you have a high resolution instrument, it's easier to put up something and to measure it on the ground correctly and to compare it to your imagery. But you still always need a few pixels to have a clean reference to do in-flight calibration, vicarious calibration. An alternative to vicarious in-flight calibration is onboard in-flight calibration. Some satellites are having some reference lamps built into their system, or which have been calibrated in the lab beforehand. Or they have a diffuser and they can look towards the sun or even towards the moon in some cases to get a solar, get an onboard calibration done based on the solar spectrum. So this is the second option to do in-flight calibration. So much about the terms. There is also maybe one term I didn't put in is the characterization. So you have to be before you do the calibration, you do a characterization. So you try to characterize your instrument, and from the characterization measurements, you derive calibration coefficients. So that's one step, maybe in between validation and calibration is the characterization. But that's for the definitions. Maybe I should add it to this graph or to this definitions later. Then two other things to consider is that you can do the calibration top of atmosphere or at sensor level. So we call this the TOA, top of atmosphere comparison. So, and we can do it bottom of atmosphere, so based on the ground measurements. And I'll try to explain this right now. So top of atmosphere is at the sensor. So what you compare is the sensor data to some reference measurements propagated to at sensor. So the top of atmosphere comparison. So this is on one hand, you have clear sensor data. On the other hand, you have to simulate somehow what happens between your ground measurement and your sensor level. So you need Motran for the simulation, or Modo or Motran to the at sensor radiance data. It has a certain there are some problems I'll outline later for that approach. On the other hand, you can do a comparison between the atmospherically corrected ground reflectance data to the ground measurements directly. So in that case, the bottom of atmosphere would be your ground spectra or your reference spectra taken directly in the field, or taken from your panels or given by the panels, and you compare it to the atmospherically corrected radiance. If looking at the situation, if you do a top of atmosphere validation, your process is a radiative transfer simulation to top of atmosphere. Critical to this approach is you need to know about the adjacency and the terrain irradiance. So in fact, if you only have your ground spectrum and nothing else, there are some impacts you cannot estimate from your data. So you need to know about the terrain, but you also need to know about the state of the atmosphere. You got to know how much water vapor was in the field or how much aerosols. So some people take out sun photometers, so atmospheric measurement devices, to know about the state of the atmosphere for such forward simulations. But it's a kind of an unknown to be fed into Motran to get a correct top of atmosphere simulation. Moreover, you have to take care of the BRDF. Well, that's always critical. And what you get as an output, it's just also a rule of thumb, is an accuracy which is in a range of about 5 to 10%. So you cannot expect to get to the 2% level of accuracy with such calibration. For validation, it's well suited because if you did that, you can directly compare your radiance measured by your system. So you don't need to do any image processing. You just take your pre-calibrated imagery and you compare against it. That's a top of atmosphere validation and maybe calibration. Question about that? If I'm going to the bottom of atmosphere validation, what you do is you do an atmospheric compensation and you get some ground reflectance. So again, we have to do the atmospheric processing. Now the critical issue is the atmospheric parameter retrieval, but you got now the advantage that you have the imagery to get the atmospheric parameters. So if you got a multispectral or hyperspectral instrument, you can derive the atmospheric parameters from the imagery, so you get a little bit better knowledge about the atmosphere. And of course, you need an atmospheric correction package for that. And how reproducible are the results? So because it's for each image, you may get a different parameterization. So it's depending on the state of the atmosphere and so on. And again, we have the BRDF problem. But in general, you are a little better off because you have from the image some knowledge about the atmosphere. Because before in the other option, we don't know much about the atmosphere itself. So in generally, it could potentially be better accuracy than top of atmosphere validation. And for in-flight calibration, one normally prefers this approach, or sometimes one does a hybrid approach. So one derives the atmospheric parameters from atmospheric correction and uses those parameters for top of atmosphere validation. And something which is always critical for both methods is what ground reference to use. So do we use laboratory spectra? Do we use in-field spectra? Do we use a calibration panel? So we have got these three options. It's never known which one to use. Now for the calibration constants themselves, the model is usually quite easy. For every sensor, you want to have a gain and an offset. well, it's not a calibration gain. We call it C0 and C1. So it's the C0 is offset radiance. It could also be a dark radiance, and C1 is just a linear relation between the digital numbers and your edge sensor signal. In calibration, the gain is just to make sure that if the definitions in calibration, the gain is usually called the relation between a signal and the digital number from the signal. So it's the inverse of this equation. Will give you the gain, the so-called calibration gain. So how much digital numbers you get from a signal, and not here, it's how much signal you get from a digital number. And we assume linearity, and often it's assumed that your system is already system calibrated. So you have removed, for instance, vignetting effects or panoramic effects to the sides and so on. So one just assumes one calibration constant per spectral band. And if there was no system calibration, so you'd see it easily if there are, for instance, banding and stripes in the imagery, or if it's getting darker to the sides. In that case, doing in-flight calibration is usually not feasible. So you'd have to put up a very complicated model to do that. You can try to estimate and fly over a homogeneous area, but with satellites, usually it's very hard to find homogeneous areas to do in-flight calibration if it's not calibrated in the laboratory before. So in fact, these two factors are a secondary calibration constant. So the first, the digital numbers are already calibrated for system effects. So these digital numbers are not raw measurements of the detector. They are already have been once transformed into a uniform image already. And to get these gains, you can do it directly on top of the atmosphere. If you do it bottom of atmosphere, you have to find a way or to translate what you get bottom of atmosphere to what's top of atmosphere. Usually it's just an adaptation of the original C0 and C1, so you see how much difference you get, and so you can adjust the two factors in the imagery. So this is about the calibration constants. Or
there's a remark you make on the BOA approach. You say is potentially more accurate for the BOA approach. Why you are saying this? I can't see why it's potentially higher. Just to...
it's the major difference is really bottom of atmosphere. You can you can calculate from the image and from digital elevation models the full irradiance, irradiant flux on the image. So you can include all the adjacency effects onto your target, and you can calculate the water vapor and the aerosol from the imagery to get a good reflectance on the ground. So in an atmospheric correction, you can consider the adjacency of your image fully for the correction. So that's the advantage if you do a bottom of atmosphere. If you do it top of atmosphere, you start with a single spectrum on the ground, and you don't know at first the surroundings. But there are methods to do this top of atmosphere as well. So you can, for instance, you can try to use from the image itself an adjacency calculation to correct for adjacency effects. But usually cannot do the whole atmospheric compensation in forward simulation. So I mentioned in the end that ideally you couple the two. So you first do bottom of atmosphere, and then you go back with all the parameters retrieved from bottom of atmosphere. You can go upwards to top of atmosphere again and compare on that level. So this is the ideal case. So maybe you make the round. So you go first, you do the atmospheric correction of your imagery, use all the parameters derived from there to do a top of atmosphere simulation, and then you can go do a very accurate comparison on top of atmosphere as well. So maybe this, the claim was not clear enough. It's not that top of atmosphere by itself is worse, but if you do it without considering bottom of atmosphere effects, then then it's worse.
Okay. Yeah. Okay. Thanks for the explanation. Yeah.
There is one thing which is also only relevant for hyperspectral is that you can do also in-flight calibration of the spectral properties of your instruments. For multispectral, this does not apply, but in hyperspectral, it's quite important to have the spectrum at the correct position. So I don't go in more detail what we use the atmospheric features in the spectrum to recalibrate the systems there. Okay, so now we're to conclude, one can do atmospheric compensation self-contained. What I mean with that is it can be run fully automatic in the meantime, so we don't need to go through estimates there. And we need accurate calibrations for the atmospheric compensation. So if you start with an uncalibrated system, you have to iterate more than once to get the good calibration. So if you want to have atmospheric characterization from the imagery and it's completely uncalibrated, of course you get wrong estimates of the atmosphere. So that's why usually one anyhow calibrates the system beforehand, and one only checks and one assumes that there were only small differences in calibration between the laboratory and the in-flight experience. If it's completely off, then it needs quite a complicated model to get back to the real good calibration constants in flight without any reference. Now for the lookup tables, we just use Motra and highest resolution. So this is no longer, I would say this is not the issue anymore. So one assumes that those are accurate in a level of below the 1 or 2%. But for in-flight calibration, we are lucky if we achieve 5% accuracy. And well, surface spectra, that's not a problem. You just interpolate. For the BRDF effects, often one has really to take a model in the background. One can use the BRDF correction method in ATCOR to get a better correction, or one has really to try to get for in-flight calibration, I mean, one has to try to get a measurement which has been taken at the same angular configuration as the image data has been acquired. Then one doesn't need to do BRDF corrections. So I think this would be the optimal case, that if you want to do in-flight calibration, vicarious calibration, you measure during the overflight, because then you have the same position of the sun and the same state of the atmosphere, the same irradiance field, and you measure from the same angle as the observer. If it's nadir looking, you just measure nadir on the ground, such that you can really do a comparison to your image. And you should measure the same area as covered by 1 pixel at least. So we usually say we want to have 9 pixels or 3 times 3 pixels of an area, and you measure in the middle the size of 1 pixel on the ground, and then you should be able to do a calibration. This is about the